Today we'll continue our discussion of these different forcing functions. What is a forcing function? Well, we're thinking of the mass on the spring problem. We've had m d squared u dt squared plus c du dt plus ku equals f of t. That was the basic equation with constant coefficients we were interested in. These don't have to be constant coefficients. This is just sort of the prototype. Then what you're really doing is saying that m d squared u dt squared, the force, is equal to f of t minus all this stuff, right? And minus c du dt was the damper. If you have a mass hanging from a spring and a dashpot damper, a damping proportional to velocity, then that's what these are. This over here, minus c du dt, is the force of the damper, and this is minus ku is the Hooke's law force of the spring. And with forces adding, we say this force plus this force, plus we can have another force. Maybe we're pushing it as a function of time with a little motor or something. And so if you're summing all the forces, we can say these are the ones that are already in the system, and this is our forcing function we're adding. It applies an additional m mass times acceleration influence. And we said in practice what can happen is those don't have to be nice, smooth functions like we've been dealing with in the past. They could have discontinuities in them, right? They might even have an instantaneous spike to infinity that results in an impulse. We call it, we have an instantaneous jump in the momentum of something. Maybe I should just mention one more time here. If this is the Dirac delta function times something, so maybe it's 2 times delta of t over here, this imparts an instantaneous change of 2 units, delta of t minus t0, at t equals t0, to m d squared u dt squared, so it imparts a change in momentum, an impulse into the system of 2 units at that time. So we've been doing those kind of functions, those and the step function. I could make you could draw piecewise continuous functions with that as forcing functions. But you can have other kinds too. You might have a signal that's periodic, for instance. Let's take a look at some of those. Suppose, what is a periodic function? You saw that in trigonometry, right? Trigonometry functions are periodic. That just means it repeats over and over, right? A function f of t is said to be periodic with period t, some positive number, or t periodic is another way to say it, on an interval. Generally you mean minus infinity to infinity, but since we're doing a Laplace transform on 0 to infinity, we'll just say it's t periodic on 0 to infinity. If f of little t plus capital T equals f of t for all little t greater than or equal to 0. So this makes it repeat every capital T units, right? Because if it's some value at 0, then it's also 0 plus t, and 0 plus and that forces at 2t and 4t and 6t to have the same value. So this repeats every capital T units. Here's an example here, a square wave, right? We had the square function last time. A single one of these, this thing that repeats over and over ad infinitum is a square wave. If you have one of these, they sometimes in physics call it a pulse, but if it goes on forever, then it's a wave. So here's the 2 periodic extension, meaning it has period 2, right? Goes like this and like this. And then it does the same thing again, like this, like this. So it repeats every 2 units on the t-axis. So this is a 2 periodic square wave, if you will. And it's equal to 1 between 0 and 1. It's equal to 0 between 1 and 2, equal to 1 between 2 and 3, 0 between 3 and 4. Wonder what the Laplace transform of that one is. Well, if you have a periodic function, it actually has a nice Laplace transform. And it has this theorem, a function that's periodic with period capital T on 0 to infinity and piecewise continuous, like this one was, right? It's actually a continuous function. Has, on each interval, each period, has transform for, at least for a real part of x greater than 0, which is all we need, f f of s equals the integral from 0 to t e to the minus st f of t dt. I thought that was the Laplace transform. Wait a minute, there's one subtlety. It doesn't go from 0 to infinity, it goes just from 0 to t, one period, over 1 minus e to the minus st. So here's the Laplace transform of a periodic function. It's very similar to what you did before. You just stop at t and then divide by 1 minus e to the minus st. And here's the proof, if you want to look at it in the notes, right? The Laplace transform of little f of t, when it's this t periodic function, is the integral from 0 to infinity, still e to the minus st f of t dt. But now to go from 0 to infinity, we could go from 0 to t and then from t to infinity, right? And we can make a substitution in there. T hat equals t minus the period. And then t, little t is equal to t hat plus the period. So we'll put that in here and here. And then this integral will go from 0 to infinity, right? Instead of from t to infinity. Because of the substitution, you have to change the endpoint. But now, integral from 0 to infinity, let's say e to the minus s capital T is just a constant. I can pull that out front. And I have e to the minus st hat f of t hat plus t dt. This is the Laplace transform of f of t hat plus t. But f of t hat plus t is f of t hat, right? So this actually here is just the Laplace transform of f, and then it's multiplied by e to the minus st, and then add the integral from 0 to t. And if you went to infinity, it would be the Laplace transform. All right, now a little algebra in here. So we'll call this f of s, that's the Laplace transform. We take this one and subtract it over to the left, right? If f of s is equal to this plus e to the minus st times f of s, subtract this over and factor out the f of s. You've got 1 minus e to the minus st f of s on the left, right? Subtract this over, factor out f of s, and then you've just got this integral on the right. There it is, divided by 1 minus e to the minus st. There's the proof. So it's nice to always see why these work. I mentioned before, I took a lot of physics classes as well as math classes, and it always bugged me that I could never figure out when those things were supposed to work because I didn't see the proof. I didn't know why it worked. So it was one of the nice things about being a math major was you could go back and look at these and figure out when you were supposed to apply them and when you couldn't. Here's an interesting problem. Find the Laplace transform of that unit square wave that we had there in the figure above, it repeated every 2 units. Well, it's transformed by the formula there, is integral from 0 to 2, because 2 is the period, e to the minus st f t dt, over 1 minus e to the minus 2s, because 2 is the period. And we just have to evaluate this. Well, f of t is equal to 1 when it's between 0 and 1. It's equal to 0 otherwise, so we can change this integral from 0 to 2 to the integral from 0 to 1, because it's just integrating 0 between 1 and 2. And then between 0 and 1, f of t can be replaced by 1. So that's how I did the top there. And now integral of 1 e to the minus st. We know how to do this one, right? From calculus 1, it's e to the minus st over minus s. And then we'll have to plug in the endpoints and take the difference. It's 1 minus e to the minus s. And then on the bottom, we've still got the 1 minus e to the minus 2s. And so now you can simplify it algebraically like that. And there's the transform, 1 minus e to the minus s over s times the quantity, 1 minus e to the minus 2s, gives you the transform of that square wave. It's not too bad a function, right? So here's another one, this sawtooth function, they sometimes call it, where it's got teeth, like a saw blade. Well, let's see. What is the equation for this one? V of t is equal to t, right? This is the line, if you call this the v-axis, this t, then this is the line v equals t right here, from 0 to 1, and then this is just an engineer's drawing, right? The real function goes up to here and it jumps down here, And this function right here just repeats over and over and over. So that's what we have, is we have a function with period 1, and repeats f of t equals t, on the interval 0 to 1, right? So, because f of t is equal to t on 0 to 1, it is periodic with period 1, we can say that the Laplace transform v of s is integral 0 to the period, e to the minus st v of t dt over 1 minus e to the minus st, where t is the period. Put in 1 for the period, put in v of t is equal to t, and put in, again, t for the period here, and we've got this. It's just a matter of doing this integral. This one is not too bad. You use an integration by parts. That's what I did to get to here. You let u equal t and dv equal e to the minus st dt. Do integration by parts. This is what you get. All this stuff. And it needs to be evaluated at 1 and 0 and take the difference. Wind up with that with a little algebra. All over 1 minus e to the minus s. So the rest of this is just algebra. But that's the idea. You just use that formula. You have to know the period, and you have to be able to do your integrals when you're done, right? Another thing that's used in a lot of the sciences and engineering is this convolution. Engineers often have a circuit or something, and they're going to hook one thing up to it, and then they're going to hook something else up to it, and then something else. They want to know what's the response when they hook up all these different things. It's a forcing function of the circuit. Remember, it has exactly the same equation as this one, just with different letters if it's an LRC circuit. So we can look at different circuits. Maybe they just have some of those components in it, and there's also, if you take second semester differential equations, you can do circuits that have multiple loops and connected together and use some of this in multiple equations. We won't get to that in this course. We'll just do the single equations. But for those, when you have something you're going to apply to the same left-hand side with a different forcing function each time, you have this nice theorem for the convolution, whereby you can do all those things quickly. And it's just sort of the language of a lot of classes also to use these convolutions. Convolution is defined this way if you have two functions, f of t and g of t, defined at 0 to infinity for Laplace transform purposes. F star g is not the composition. We use that for composition of two functions in algebra, but here it's going to mean the convolution. The convolution of f and g of t is the integral from 0 to t of f of t minus tau g of tau d tau. So this actually comes out to be a function of t, right? There's t up here at the top of the integration, and also in here. And tau is a dummy variable. You can put u there if you like. It just falls out when you do the integration. But that's the definition of the convolution, and it's not too hard to show. I think I have it here somewhere still. But the f convoluted with g is the same as g convoluted with f, so just like it looks like maybe it's commutative, it does have the commutative property. You can put these in either order and the integral comes out the same. Alright? Yeah, there's the proof right there. Okay, so let tau equal t minus, that should be t hat. Oh, tau hat, yeah. Tau equals t minus tau hat in the integration there. And here's convolution of g with f has this definition, and then you replace tau with t minus tau hat, and so f of tau becomes f of t minus tau hat, and d tau becomes minus d tau hat. There, it's taking the derivatives there. And now, if you switch the order of integration, that puts another minus in there and cancels out this minus. So you get g of tau hat, f of t minus tau hat, d tau hat, with the minus canceling the switch of the integration order. There it is. That's the convolution. F with g. So g convolution with f is the same as f convolution with g. There's the proof. Now, if f and g both have Laplace transforms, suppose they're called f of s and g of s, at least for a real part of s greater than some number alpha, right? Then for the real part of s greater than alpha, the Laplace transform of the convolution, this is the convolution theorem, is just the product of those two convolutions. That's the amazing thing that makes this so useful. This integral, why would you want to do a nasty integral? It's because the Laplace transform of that integral is actually the product of the transforms of f and g. A lot of times you get to the end of the problem and you say, boy, I recognize that transform, I recognize that one there, but what is the inverse transform when two transforms I know are multiplied together? This gets it for you because you go backwards and say, if I have two transforms multiplied together that I recognize, the inverse transform is just this integral f convolution with g. So here it's written out here. If you want the inverse transform of the product of two transforms you know, it's just a convolution. That's the big use of the convolution theorem. So suppose we find the inverse transform of this one, just as a simple application. Sometimes this is useful in inverting things because you recognize, look, 1 over s squared, 1 over s squared plus 1, those are transforms I recognize. 1 over s squared plus 1 is the transform of sine t. 1 over s squared is the transform of t. Boy, it's not the transform of t times sine t though, right? Instead, it's the transform of t convoluted with sine t. That's what happens. When you see the product of two transforms you know, that means the function that has that transform is the convolution of those two that you had. So here, this f of s is the convolution, is the product of 1 over s squared, the Laplace transform of t, and 1 over s squared plus 1, the transform of sine t. So by the theorem, the inverse transform, the second part of the theorem, the inverse transform of the product is the convolution of the two functions that have those transforms. So it's f of t is t, so f of t minus tau is t minus tau. And here's g of tau, d tau, integrated from 0 to t. So you just have to evaluate this integral. It's easiest to break it up into two parts. And here's a nice thing, t is not the integration variable. So if you break this up into two integrals, t sine tau and tau sine tau, subtracted, the t can come out because it's a constant. So this one's a little easier. Integral of sine is easy, right? Just minus the cosine. And then integral tau sine tau is a little harder. You can't pull the tau out. It's not a constant here, right? It's the integration variable. But we can use integration by parts on this one and get this one. And it comes out like this. Sine tau minus t. Let's see. Sine t minus t cosine t is what it comes out to be when you do the integration by parts and plug in the endpoints. And so this whole thing just comes out to be t minus sine t has this transform. And you can get that back by taking this transform. You'll get two quotients, and when you put them over a common denominator, you see you can return this. So nice thing here is you must check your answer. Just take the transform and see if you can put it in that form. Well, one last comment. We've got a lot of transforms and a lot of theorems. Who can keep track of all that stuff? What did you do when you had integrals? This is an integral, right? You made a big table of them so you can remember. In this case, I use this. In that case, I use that. Kind of have it together in your mind which way to go. People build big tables full of Laplace transforms too, right? The transform of 1 is 1 over s. We did a little short table. Those are the ones you should memorize. That'll help you in the long run if you're one of those people in some science